Hello and welcome back to Fullerton College's pre-press class. This is Professor Ben Kiewit. We are picking up on what is hopefully the last video, although I can talk for ages, as you're starting to notice, on this subject of the color appreciation chapter from our PIA training manual. Here we are, we're looking at subtractive color. I know our last video ended on this, but I'm going to pick up here because for me, it's the next day. Anyways, here we are as a demonstration of how this works. Subtractive color. Whatever your light source is sending hopefully an even amount of red, green, and blue light to your eyes. And that color of light reflects entirely, or mostly, there is no such thing as 100% in real life, guys. It doesn't really exist except in theory. Very nearly most of that light comes back off the paper. And if the paper is clean and white, you'll see all the colors of light that you saw from that light source reflecting off. Now, if we put a cyan filter, which is to say if we print cyan colored ink on top of that paper, then the white light source hits the paper, the green and the blue light bounce off as normal back to your eyes. But the cyan filter appears cyan to us because it absorbs the red light. It is removing red from the three primaries that we normally see. So when your eyes and your vision system see green and blue light but does not see red, both the combination of green and blue and the absence of red cause you to experience the color cyan. So that is why the ink is cyan, and that's what it does. Here's the two other obvious examples that we're going to necessarily follow, logically speaking here. So again, you got your white light with all the colors. If you have magenta ink on your paper, that magenta ink absorbs and stops or filters out, captures, traps. I mean, I could go on the thesaurus all day if we really need to. But anyways, it removes the green light from what you're seeing, and all you see are red and blue. And when you see equal amounts of red and blue, but no green, you see magenta. And then there's yellow, as seen in our this video is not yellow video. Red, green, and blue light hit the paper. The yellow colored ink absorbs the blue light because yellow and blue are opposites, and bouncing off, you get red and green. And to your eye, when you see equal amounts of red and green, why, that's yellow. So the subtractive process, remember that you're subtracting part of it, you can follow this. Now, actually, this is not the best way to remember it. Let me pause for a moment. We'll jump back. Actually, we'll not even pause. Let's jump back a bit here. This is the best way to remember it. In fact, you can even draw a quick little diagram out just using the RGB and CMY abbreviations for these colors and make yourself a little color circle. The color that is directly opposite removes it on this circle. So you see that cyan is across red from black. Magenta is across green through black, and blue is across yellow through black. So yellow and blue are opposites. Yellow subtracts blue, cyan subtracts red, and magenta subtracts green. It's easier visually. They want you to do it through just memorizing, and it's much easier to do the diagram. If I have to remember it, honestly, guys, I will doodle out a little diagram. So cyan removes red, magenta removes green, and yellow removes blue. I do like this, however, for saying most. There is no such thing as a pure ink. There's no such thing as a pure color, not in the real physical world. Everything we make has to come from somewhere, whether you're talking about if it's organic or inorganic or artificial or chemical, created in a lab, however you want to look at this stuff, the material is coming from somewhere. Even if you have the most artificial color in the world, that artificial color is something we made by digging up minerals and harvesting plants and animals on this planet. We don't do animals very much for color anymore. That's more of an old world thing. Sorry, guys, a little outdated on that one. In fact, that's why there's almost none of certain mollusks left, because they made a beautiful purple, and they were harvested for that back in the days of ancient Rome. And now you can barely find them. They might even be fully extinct, but that color is kind of gone. Anyways, the point is, even for that beautiful purple from ancient Rome, that came from somewhere on Earth. Even for the most bright fluorescent color you can possibly make out of ink, those chemicals come from things we find on Earth, and nothing is 100% completely pure. There's always, it's the cleanest color we can find, but dyes and pigments have to be made out of objects, have to be made out of substances that we find on the planet and process. And you could do a lot of processes to remove as many impurities as possible, but no ink is actually all the way pure. In fact, different manufacturers of printing ink, their colors are a little bit different. Personally, I see the differences mostly in the blacks because black is supposed to be neutral. Therefore, it shows the most variation. But again, just as I talked about in the past, magenta ink can be a little bit red or it can be a little bit purple. Yellow ink can be a little bit green or it can be a little bit orange. Cyan ink can be a little bit more blue purple or it can be a little bit more green. And that does still mean that on any given press with any given set of inks, you might have a weak part of your gamut that's harder to reproduce than the other side based off of how your inks lean. It's called color cast. So it's called process color. Cmyk is process, process is Cmyk. Normally, we use this. We represent, we reproduce, we do not recreate, we do not copy exactly, but we reproduce, we make very good approximations of most colors using mixture is not exactly the right word. We'll get into halftones later in another chapter, but using screens of dots that remove the right proportions of color, our eyes still see the overall view as saying, if you have little dots of yellow and little dots of cyan next to each other and you're far enough back, it's removing that red light and it's removing that blue light. What you're getting back is green. Anyways, so they still absorb part of the light and let you see what's remaining. Again, don't forget that the color of the paper matters too. Here's another one of those good nuggets to learn here. What does color consist of as we see it? It consists of the lighting conditions. It consists of the object you see in front of you. And it consists of your eyeball and your visual system, your eye, your optic nerve, how your brain, or more scarily, somebody else's brain who you don't understand their experience of, you never really can. You don't see how someone else sees. So those are the three variables that determine how we experience color. We can control two of these, but we cannot control the third. You can never control how someone else sees it, but what you can do is eliminate the other variables. You can make sure that the lighting is good and consistent. You can make sure that the objects are set up correctly or photographed correctly, and make sure that the color or the inks being used on that paper, the color of the paper is consistent. So one of the difficulties also is describing color because it's a sensation, because color is an experience, a phenomenon that we are having. And because it is therefore related to our own individual biological selves, we have to try and describe it, but it's sometimes difficult because it's the same as describing how something tastes to you. And I believe, at least in English, taste has one of the least amounts of vocabulary, by the way. English does not describe taste very well. There are categories of flavor that have specific names in like Japanese that don't translate to English because we just say, it's salty, it's sweet, it's sour. And we kind of leave it at that. You can say savory, but there's not a whole lot of very specific things. In fact, one of the fun things to do is to read wine labels and hear them try to describe flavors of wine. And my roommate from high school, sorry. Wow, I didn't have roommates at high school. Those were called siblings. Back in college, one of my roommates' games was you read the back of a wine label and use it to describe a fart. Floral, but with peppery notes. Anyways, flatulence aside, trying to describe things like smell, taste, touch, hearing are not that different than trying to describe color because you're describing your interaction with it, your interpretation of it. And this leads to some problems because you end up with words that are not by nature objective. They're all subjective because the color itself is subjective. It's something that you are experiencing. So people will say things when they're trying to talk about colors. It's kind of flat. It's kind of muddy. It needs more snap. Oh, it's too warm. It's too cold. I actually like warm and cold. Those are good descriptors, but that's just my personal taste. Make it jump off the page. And I'm going to do it here. So let's write the word that I hear all the time from clients. Make it pop. This is a very common one now. It's gotten popularized on like Instagram and stuff. And my wife asks me not to disparage people who use this language because honestly, you don't necessarily have the language to describe this stuff. Typically what they're looking for with pop or snap or jumping off the page is they're really looking for high contrast, both in light to dark and also in chromatics. So the colors are very high contrast, typically speaking. Anyways, let me clear these and move on. So color viewing conditions. Again, we talked about this a second ago. Color viewing depends on the light source the object you're looking at and the person seeing it. You can't control a person's experience, but ideally, at least in person, you can control the lighting and you can control the object they're seeing. So if you make sure you have a standard lighting condition, then you can do this. In fact, there is one. There is a standard lighting condition. Whoa, whoops, there we go. The American National Standards Institute, ANSI, has standardized viewing conditions. This is the North American one. There are other standard viewing conditions on other continents. Anyways, we're looking for a light that has the color temperature of 5,000 Kelvin. That sounds extreme, but honestly, it's just saying about if you're describing a brightness. We'll get into that in a second. And they also want the surround, the space behind, to be painted in a neutral Munsell NA gray paint. I still think at one of these days I'm going to have to paint my workbench where I do my modeling, and I model building, guys. I'm not that kind of model. I'm a model maker. I'm dorky and not that good looking. Anyways, that's where I do my modeling, this color, and I would love to get some of our classrooms repainted in this extremely dull and boring color. It's dull and boring for a reason, because the color next to you affects how you see things. The two things that matter, the two things that you can do if you're showing someone something, you want them to see it for itself, is to remove other context by isolating in a gray environment with no other things, no posters, no pictures, no badges, no weird colors anywhere. All you're seeing is the print in one of these booths, if you do it right, with properly tuned lights that give the right spectrum of light, as close to full spectrum as possible. Excuse me, sorry. So here's the thing to prove that the colors next to what you're seeing matter. This is a fun trick the PIA has. I have a hard copy of this in my lab too. So let me prove to you that these are the same things. You can see this green is the same color in both places. Well, you can't see it. In fact, it looks like the green over here is dark and the green over here is light. It has to do with what you're comparing it to. Your brain, your eyes want to compare colors to what's next to them. Let me go ahead and open up my print production here, whip out my output preview. And this is a tool, which we'll go into more detail in this class later on, that lets you see what the Cmyk build of any image, any pixel on the screen is. Where I move my cursor, you can see in the box on the right, the preview box, it tells you what colors they are. For instance, this deep blue is 89% cyan and 72% magenta. That's the mix. Yellow is 96% yellow. It's not 100 even, it's 96%. The green over here is 40% cyan and 100% yellow. And over here, it's, by contrast, 40% cyan and 100% yellow. So in fact, they're the same thing. So we've established they're the same color. Let me scroll to the next page for you. And now look, the right column seems to have gotten much darker. Let's see if it actually has changed. The right column is 40% cyan and 100% yellow, but the left column is 100% yellow and 40% cyan. I'm saying that funny, but they're the same thing. The difference between this and this is simply the context. This is why a neutral viewing booth is so good. I also have to humble brag here, although it's no longer true. I have to say used to, past tense. I used to have friends, well, period. Thanks, coronavirus. No, but I used to have friends who worked at Blizzard Entertainment down in Irvine. Yeah, the Warcraft people. And they've moved on to other jobs since then. This is now years ago. I'm getting old and everything I talk about is past tense now. Anyways, I visited their offices and their desks are absolutely piled in little swags and toys and things. And it's really cool and very personal, but their desks are not where you want to see color and try to understand what color you're looking at, because they are covered in piles of Legos and Funko figures and posters from movies they like, sometimes stacked to the ceiling on top of their cubicles. Anyways, that is the opposite of a good color view. Good color viewing gets rid of the surround, because when all you have is a gray booth, then the only thing you have to compare to is other colors in the print job. That way the relationship between the colors you printed is shown, but not the relationship between what you printed and your favorite Funko Pop toy sitting on the desk next to it, because that will actually ruin your ability to see it for what it is. All right, well, I hope to finish this in one more video, but it looks like we have one more video. This is in fact the penultimate. Stay tuned for one last video on color appreciation. In case you're wondering, I do appreciate color.